So, we are close to the end of this course on classical mechanics. I had done some problems on rigid body rotation about a point using Euler's equations of motion, and I will do some more problems before finishing the course. Now, today first of all I will show you some demonstration. I have this notebook. So, it is essentially a rectangular plate, it is like a rectangular plate with some thickness, and if I use the center of mass as the point origin, then very easy, 3 principal axes, one along the length, one along the width and one vertical perpendicular to this plane. So, these are the principal axes. Now, what I will do is I will rotate it about a principal axis, one of those 3 axes, and then let it fall. So, it falls under gravity. So, that mg is acting, but that mg does not have any torque about the center of this plate of this notebook, and so no torque is exerted by that mg, and hence as far as the rotations are concerned, we will have as a 0 torque situation. The center of mass will fall, x is equal to half gt square and all those things, but then the rotation is still guided by our equations of rotation. So, first look at this. I will be rotating about this axis perpendicular to this bigger face, flatter face. So, this axis I will be rotating, and you notice how it falls on the table. Okay. Once it falls on the table, that means once it has travelled this much of distance, what has happened to the angular velocity? Initial angular velocity will be along this say one direction, and other omega 2, omega 3 I will try not to give, okay. And if finally when it reaches the table, whether it is still in this plane or it has tilted. So, that is the thing to see. So, watch. All the time its face, this face, the lower face hits the table, okay. It goes like this, it rotates and then it hits like this. Natural, this is a principal axis, and if you rotate about the principal axis, then class 11 mechanics is fine. So, it keeps rotating about that axis and then it just reaches the table and falls. Now, I will be rotating about this principal axis. This is also a principal axis. About this principal axis I will be rotating, and then carefully watch what portion of this notebook hits the table first, whether it is this part or it is this part or it is this part, which part, this edge hits the table or this edge hits the table or this area hits the table. Careful. Okay. So, all the time you are seeing that this edge is hitting the table, this edge, this whole thing may not hit, it may go like this or it may go like this, but this edge is hitting once again. And now, this is the part for which I am doing this demonstration. This is the other axis. So, say one axis, then 2 axis and 3 axis. So, about this I will be rotating, and carefully watch what portion of this plate or this notebook hits the table. Okay. So, when I am rotating, it is not this edge which is hitting the table. Alright, most of the time this surface hits the table. I start with this orientation. The angular velocity is given in this direction. So, it should go like this, but somewhere it has gone like this. Somewhere during the path it has rotated and the flat part hits the table. So, that means this rotation means this is picking angular velocity about this, then it will rotate like this. So, although I am giving initial angular velocity along a principal axis as best as I can, of course, this is a very crude method of giving initial angular velocity, but there is something special about this, that it picks up the other rotations very fast. So, let us do this problem, let us analyze this problem. So, I have this plate, and then there is some thickness, and the three axes are, one is here, call it I1, one is here, call it I2, E1 direction, well, yeah, one axis, this is one axis, this is two axis, and then perpendicular is the three axis. What are the equations? Using these as the axis system, this is fixed in the body and then they are principal axis also. So, I can write the Euler's equation I1 omega 1 dot plus omega 2 omega 3 and then omega 3 I3 minus I2 is equal to tau 1 and which is 0. We do not have any torque. So, this is the equation. So, I1 omega 1 dot is equal to omega 2 omega 3 and then I2 minus I3. Similarly, I2 omega 2 dot will be omega 3 omega 1 and then I3 minus I1, and I3 omega 3 dot will be equal to omega 1 omega 2 and then I1 minus I2. Suppose I start with giving omega 1. So, our initial angular velocity is largely, omega is largely say omega 1 E1 and omega 2 omega 3 may be there small, very small, all right, because I try to give it a pure rotation about one principal axis. Of course, I cannot do it so crudely. So, some omega 2 omega 3 may enter, but suppose it is very, very small. So, what do I see from here? This omega 2, this omega 3 is very, very small, and therefore, omega 1 dot is very small, and hence omega 1 is nearly constant. Okay. So, if I say is this 1, this is 2, this is 3, then what we will say is from 1, since omega 2 into omega 3 is very small, this omega 1 dot is also very small, and hence omega 1 is nearly constant, and whatever angular velocity I had given initially, it will largely, that component will largely remain there. This first component omega 1 will be nearly constant, equal to what I had given initially. Now, look at these two equations. This is I1 omega 1 to, okay, right, this is 1, this is 2, this is 3. So, look at these two equations, these ones. What does it say? Omega 2 dot. Omega 2 dot, initially I have given a very small omega 2, but then omega 2 dot is dot is equal to omega 3 and then omega 1 here, I 3 minus I 1 here, and divided by I 2 here. Okay. Omega 2 dot is omega 3, omega 1, I 3 minus I 1, and then divided by I 2, and from here you have omega 3 dot equal to omega 3 dot equal to omega 1 omega 2. So, it is omega 2 and then omega 1. So, I have written omega 1 omega 2 I 1 minus I 2. So, I 1 and minus I 2 and divided by this I 3 by I 3. So, these are the equations, and omega 1 is nearly constant. So, that is why I have written it here and I have written it here in this bracket. Let us differentiate this one. What is omega 2 double dot? Omega 2 double dot is equal to omega 3 dot, and this is nearly constant. So, it is omega 1 I 3 minus I 1 by I 2. Okay. Omega 2 double dot is omega 3 dot and then this quantity, and omega 3 dot is here, this omega 3 dot is here. So, let us put it there. So, this is equal to omega 2 here, I am trying to write this from here, I am writing this from here, and this is omega 2 omega 1 I 1 minus I 2 divided by I 3. So, I have written this part and now this part, omega 1 I 3 minus I 1 divided by I 2, this part. So, omega 2 double dot is equal to omega 2 into some this whole thing, let us write something. Okay, omega 1 square I 1 minus I 2 into I 3 minus I 1 and then divided by I 3 into I 2. Okay. So, omega 2 double dot is equal to omega 2 into omega 1 square I 1 minus I 2, I 3 minus I 1 and I 3 I 2 here. Now, this quantity, let us look at this quantity. Let us look at this quantity. It is like constant, omega 1 is almost constant. So, it is like a constant. Now, if I 1 is maximum of the 3, if I 1 is maximum of the 3, then I 1 minus I 2 will be positive and I 3 minus I 1 will be negative. So, this whole quantity will be negative, and I can write that as omega 2 double dot equal to this omega 2 double dot equal to omega 2 into this negative quantity, which I can write as say minus alpha square omega 2. And you know what this equation means. This means omega 2 is oscillating with some amplitude. This is simple harmonic motion type equation for omega 2. So, this means that omega 2 is oscillating with frequency or angular frequency alpha. And since initially omega 2, omega 3 were small, I did not want to give any omega 2 or omega 3, but it did crept in there. Then or from disturbances of air or some other thing in the path also, it can pick up some small omega 2, omega 3. So, the amplitude will also be small, so with a small amplitude. And same will be the case with omega 3, same with omega 3. Okay. So, largely it will continue with angular velocity omega 1. Some small omega 2, omega 3 will be there, but that will be oscillating, the amplitudes will be small, and finally, when my notebook falls on the on this table, it falls with that initial, whatever was initially below this surface, it falls there if I 1 is maximum. In fact, if I take this as the axis, the moment of inertia will be maximum as compared to this axis and this axis, because this is perpendicular axis theorem, this will be sum of this and this. So, if I am giving it this rotation, that means I am in this I am satisfying this condition, I 1 is maximum. What if I 1 is minimum? Okay. If I 1 is minimum, if I 1 is minimum, then what happens? This is minimum. So, I 1 minus I 2 is negative, because I 1 is minimum, but I 3 minus I 1 is positive, because I 1 is minimum. So, this is again negative. So, the same story is the same story again omega 2, omega 3 will oscillate with small amplitude. That means motion is stable. Okay. I had given angular velocity about omega 1, even if it picks up some omega 2, some omega 3 little bit, that is not going to disturb the motion too much. Largely it is still rotating about that one axis. Now finally, if I 1 is intermediate between I 2 and I 3, it is intermediate between I 2 and I 3, then if one is positive, other will be also positive, if one is negative, other is also negative. Okay. If I 1 is in between and I 2 is the largest, suppose I 2 is largest and this is in between, this is the story, then you can see I 1 minus I 2. So, this is smaller, this is larger, so this is negative, and I 3 minus I 1, I 3 minus I 1, this is smaller, this is bigger, again negative. So, this will be positive. Same will be the story if it is the other way. So, if I 1 is intermediate between I 2 and I 3, then this factor here is positive, and if this factor is positive, you can write your equation as omega 2 double dot is equal to alpha square times omega 2. And you know the solution. You know the solution of this equation also. It will be like e to the power alpha t, and the other term will be e to the power minus alpha t, but this will not dominate, this will dominate. So, it will keep increasing. Okay. Omega 2 will keep increasing, because omega 2 will be some constant, although this is a small constant, initially it is very small, say e to the power alpha t, and some b e to the power minus alpha t, ultimately this dominates. So, initially the value is small, but this is continuously increasing as time passes. Okay. And therefore, omega 2, even if what initially small, it will keep increasing, it will keep increasing. Same will be the story with omega 3. So, this is not stable. So, when I am rotating it this way to start the motion, I am using this intermediate, my this moment of inertia of this plate about this is intermediate between about this and about this. This is the smallest. This is the smallest, masses are close to the axis. Then this is little bit larger, okay, that m L square by 12, m b square by 12, and then this is sum of these two. So, that is what you have seen. If I am doing this rotation and then letting it fall, as time passes it is picking up the other rotations, and finally in some situations when it is rotating about this axis, then it becomes stable and it falls on the table that way. So, this is about stability. So, before taking up the next problem, let me give the demonstration of the situation which will be there in that problem. And that is, I have this wheel and I have an axle here, this is an axle, and then a rope is tied to this end and I am holding it here, okay. And then this wheel will be spun, I will be giving a spin angular velocity, it will spin like this. So, let us do that and see what happens. So, this plane is vertical and then I am giving a large velocity, and you see the wheel is spinning and is also rotating about this about the vertical line through this support here, okay. Once again, so the wheel will keep spinning, that is one. At the same time it will rotate like this, it will rotate like this, right, and if this speed is high, it will remain vertical, almost remain vertical. See once again. So, there is a precision. So, now the problem is the same situation which is written here. A wheel of mass m has moment of inertia I naught about its symmetry axis. So, I have a wheel and this is the symmetry axis, and the moment of inertia about this axis, which we will call, let us say 3 axis, is I naught. A light axle is attached to the center. So, I have an axle here, light, okay. So, this is axle, this line is our geometrical line, right, to show the axis. This is the actual physical axle there, and then the other end length being L. So, this length is L. The other end of the axle is tied to a light rope fixed at some support. So, this is a rope, and that I was holding here. So, this is that fixed support, this point is fixed. Initially the rope is nearly vertical. So, initially the rope is nearly vertical. So, this angle is beta, let us say small, nearly vertical. The axle horizontal, this is horizontal, and the wheel spinning with large angular velocity omega naught, okay. So, it is spinning with large angular velocity omega naught, that is given. The wheel axle system moves under the gravity and of course, this tension, right, gravity, you can write, and the tension from the rope. So, these are the forces on this wheel axle system. Assume that it precesses with a uniform angular velocity about the vertical line through the support. You had seen that this is called precession, this motion is called precession, this is called spin. So, it is precessing with a uniform angular velocity, and that the spin velocity remains constant. So, you assume that the spin velocity omega naught, that remains constant. Now, you have to find the angular velocity of precession and find the angle between the rope and the vertical, assuming it to be small. So, this is our question. So, let us choose axis system. So, this I will be using as 3 axis, and vertical from here I will be using as 1 axis, and then horizontal in this plane of the disc, that I will be using as 2 axis. These are principal axis because this is perpendicular to the wheel, it is a symmetrical system. So, this is a principal axis, then this is a diameter, Okay. So, you assume that it is all symmetrical, and this is principal axis, and then this is also a diameter. So, this is also principal axis system. So, this 1, 2, 3 is principal axis system. Principal axis 1, 2, 3 are principal axis, but they are not fixed in the body. It is not body fixed frame. Why? 3 is all right, 3 is all right, all the time it is normal to this disc, plane of the disc. So, this is all right, this is fixed, but this I am saying it is vertical, and at different times different radii will come here. This time this particular radius is vertical, but now the disc is rotating. If the disc is rotating, let me rotate it this way. If the disc is rotating, then this radius, which was not vertical, will become vertical after some time, and therefore, this one axis is not fixed with the body, 2 axis is not fixed the body. So, it is not fixed in the body. So, if I use these axes, I cannot use Euler's equation of motion, because Euler's equation of motion are based on the assumption that our principal axis 1, 2, 3 are fixed in the body. Okay, that is why that dl dt in body, so that those things are calculated with that assumption. So, we will not be using that. Torque is equal to dl dt in inertial frame, and then this is equal to dl dt in rotating frame, which may not be fixed with the body, and then omega cross L. And what omega is this? What omega is this? This is very important. What omega is this? I should not use this symbol. So, let me use another symbol, capital omega. This is angular velocity of the frame, of this rotating frame. With respect to the inertial frame. All right. So, we have done that. So, we have chosen the 1, 2, 3 axis rotating frame of reference. This frame is rotating, and if I look from the lab, from the inertial frame, this origin is also going on a circular path. Okay. So, this equation, when we derived, that time our origins were same. Now, this origin is also going on circular path. So, that also we should take into account. So, what I do is I use another frame, say XYZ frame. Let me use another frame, XYZ frame, and what is the description? XYZ axis coincide with 1, 2, 3 axis, 1, 2, 3 axis, coincide with 1, 2, 3 axis at t equal to 0. Okay. After that, the directions of XYZ remain fixed in the lap frame, which is inertial. So, carefully see what this XYZ frame at t equal to 0, this is x, this is y, this is z, fine. But after some time the wheel goes somewhere else, this goes somewhere else, and the axis 1 axis, 2 axis, 3 axis, they are all rotating. If the wheel is going from here to here, this 3 axis, for example, this 3 axis is also going, it is normal to the disk, but our xyz axis, the origin will go, the origin is here, okay. Origin of this xyz frame is at the center of the wheel, same origin as for 1, 2, 3. Origin will change, but the direction will not change. If this is axis, the origin has gone here, this is the x axis. It comes here, this is still the x axis. X axis, y axis, z axis will not change orientation, 1, 2, 3 axis can, right. So, that is how we have we are defining xyz frame. Now, can I use this xyz frame as an inertial frame of reference? No, because ultimately the origin is going in a circle, each point of the frame is going in a circle, right, different circle, but same with the same radius, and therefore, it is a translation of the frame. We had discussed it earlier when we were doing non-inertial frames, rotating frames. It is a translation of the frame, and we only have to use pseudo forces. If I want to use this xyz axis as inertial frame, I only have to use pseudo forces which are mass of the particle into acceleration of this frame, and that acceleration is same for all points of the frame. It is just that whatever origin is going with some angular velocity capital omega, omega square times this radius of that circle and in opposite direction and so on so on. Important thing is, for all particles of mass m, wherever they are situated, for all those particles, if the mass is m, the pseudo force is same, mass into that acceleration of the frame, and therefore, the torque of all those pseudo forces about the center of mass will be 0. That is how the center of mass is defined. mg, all particles, mg, and if you take torque of all those things about the center of mass, 0. Similarly, here the pseudo force m into a naught, m into a naught, m into a naught, m into a naught. If you take the torque about the center of mass, it is 0. So, although it is not an inertial frame of reference, but as far as the torques are concerned, I have taken care of pseudo forces. So, I can treat it as inertial frame of reference, and those pseudo forces have no torque, and so I can directly use this. This can also be written as dl dt in xyz frame. Okay, dl dt in xyz frame is equal to dl dt in 1, 2, 3 frame. This is our 1, 2, 3 frame, and then plus this. So, let us write our equations. This omega with which this frame is rotating is omega times E1 cap. This vertical is E1 direction, and this whole frame 1, 2, 3 frame is rotating with an angular velocity of capital omega, which is the precession velocity. So, with this velocity it is rotating. I am putting the origin here, so it is rotating at its own place like that, but the angular velocity will still remain that omega. And for any particle, and that means for this whole object, this whole wheel axle system, omega will be equal to omega 3 or omega naught in E3 direction, correct. This is that spin omega naught in E3 direction, that remains constant, we have assumed, and plus this omega E1. So, this is our omega for this body, and therefore, when we write L, this L is written as, in 1, 2, 3 system we will express this L, but remember it is L is L, vector is vector, In any system you can write the components. So, this L is equal to I 1 omega 1 E 1 cap plus I 2 omega 2 E 2 cap plus I 3 omega 3 E 3 cap. So, this is how we can write, because 1 2 3 are principal axis, because 1 2 3 are principal axis, therefore, we can write that. And then omega has 3 component, omega has 1 component and no 2 components. So, this is equal to I 1 and omega 1, yes, omega 1 is there, capital omega E 1 cap. This is not there, omega 2 is 0 and this is there, plus I 3, I 3 is that I naught, I 3 is that I naught, and omega 3 is omega 3 is omega naught E 3 cap, correct. So, this is L, this is our L vector, and then we write this dl dt torque, and torque is equal to dl dt in inertial frame of reference, which is same as dl dt in xyz frame of reference. So, that, and this is equal to, so this is inertial and this is equal to, in 1 2 3 frame you can see that no component is changing. Okay. So, when you write dl dt in this 1 2 3 frame, this part is 0 and therefore, it is this part, and this part is equal to omega E 1 cap cross L, and here is L. So, let me make some space and then we write it. So, our equation was torque was equal to that omega cross L. So, this is omega and then cross L, and L is the first component was I 1 omega 1 E 1 cap, second component was 0 and the third component was I 3 omega 3, which is I naught and omega naught E 3 cap. This is what we had derived so far. Now, we work on this. This is equal to, this part is 0. So, it is omega here, I naught here, omega naught here, E 1 cap cross E 3 cap, which is minus E 2 cap. Now, the torque is coming from where? The forces. And what are the forces on this wheel axle system? The forces are gravity mg and then this tension T. These are the forces which are acting on this wheel axle system, for which we are writing all the equations, and we can write torque about the center, about the origin, and therefore, torque of this mg will be 0 and you only need torque of this T about this origin. So, it will be R cross F. Remember torque R cross F, R cross F. What is R here? R is this vector. This is R. Here is the origin and here is the force. So, this is R. This is R. You write it as L and minus E 3 cap. Correct? It is in this direction, minus E 3 cap. And then cross product with this tension. It has 2 components, one is in this direction, one is in this direction, and this component is T cos beta. So, T cos beta, what direction? E 1 direction, that is the one direction. So, E 1 cap, and T sin theta will be 0 because it will, that is passing through the center. It is this, and this is equal to, you see, this E 3 cross E 1 is E 2. So, it is minus and L here, and then this tension cos beta here, and then E 2 cap, right. This minus is here, E 3 cap cross E 1 cap is E 2 cap, T cos beta here, this L is here. So, this is the torque, and from this equation torque is this capital omega I naught omega naught minus E 2 cap. So, see the directions are good, minus E 2 cap and minus E 2 cap, and therefore, the magnitudes are also good. L into this L is length okay, this L is length. So, let me write it small l, let me write it a small l here. So, it is L, and so this is L here. So, small l into length into this T cos beta is equal to omega and I naught and then omega naught. So, this is one thing. Then there is a equilibrium in vertical direction. Okay. This whole wheel axle system, the center of mass is going on a horizontal circle. So, in vertical direction there is an equilibrium, and therefore, this T cos beta should be equal to mg, right. So, T cos beta should be equal to mg because of the vertical equilibrium, and therefore, this equation now becomes L into m into g is equal to capital omega I naught omega naught, and therefore, capital omega is equal to m g L divided by this I naught omega naught, I naught omega naught. So, this is the answer of part A. This is the part A answer. What is the find the angular velocity of precession? So, the angular velocity of precession is mgl divided by I naught omega naught. More is omega naught, higher you spin it, and then you will have lower angular velocity, it will go slowly. If you spin it fast, it will go slowly, it will precess slowly. If you do not give that much of spin, then it will go faster. So, that is this from here. Now, the second part is find the angle between the rope and the vertical, that means find this beta. So, now this component, this horizontal component is T sin beta. This is T cos beta this side and T sin beta this side. What is this sin beta doing? This is providing the centripetal acceleration, because the center of mass is going in a circular path, and therefore, the net force on the object must be mass of the object into acceleration of the center of mass, and therefore, this provides you the centripetal acceleration. So, T sin theta should be equal to, and that you know how much it is. T sin theta is a force, and that is mass into omega square into radius, and radius is L plus, this is the center of this circle. So, L and plus, if this distance is d, okay, if this distance is also needed, if this distance is d, it is d sin beta, d sin beta. Okay. And T you can again write from here what is T, and then things can be written there, but let me do this is beta. But let me use this approximation. Sin beta is beta and cos beta is 1. Remember 1 minus beta square by 2, that is why we can take it 1 if beta is small, sin beta is beta. Then this becomes T times beta is equal to m omega square and then L plus beta times d. And this equation here, T cos beta equal to mg, under that approximation T is equal to mg. So, T equal to mg, and therefore, mg beta is equal to m omega square L plus beta d, and from here you can write, you can collect these two beta terms together and then solve it and get beta value of beta. So, we will stop here, and next class we will take maybe one more problem, and then we will finish the course.